This is remodeling elderly walkers to improve walking conditions by replacing arm-based support with pelvic support. The problem is that mobility restriction is a major issue within elderly populations globally. Modern walkers and mobility assists were created to help take weight off the hind legs, however, at the cost of adding new stress to the upper body, causing upper limb disorders leading to shoulder injuries and related complications over time and extended usage. Background research involved going through the market to review existing solutions and reviewing studies that explored how these solutions support the user's weight. Modern mobility assistance centralizes around arm-dependent support or complete body support, such as a wheelchair. Currently, no devices exist as an intermediary, which use standing body support without the need for arm posting. The goal of this project is to create a design that does just that, hold the full seated weight of a 240-pound user, demonstrating that the user can be fully supported without putting any weight on the hands or elbows, while also allowing the user to stand. The requirements of this project is that no human testing is allowed, and the design must accommodate the 5th and 95th percentile human measurements, as well as any other requirements set by the CDC. The prototyping process was long and extensive and was initiated by constructing prototypes based off of design sketches. The first iteration underwent a dimensional failure after exceeding CDC guidelines for hallways and needed to be reduced in size. The second iteration met the dimensional requirements, however only at the minimal weight setting. It failed the weight load test, getting damaged at the width adjustable parts, and in the third iteration the width adjustable parts were removed, given that only the minimum setting was necessary, and was replaced with a solid frame for strength. It successfully met the dimensional requirements and passed the weight tests. The final design is a walker frame designed to surround the user with swivel wheels for mobility. Attached to the frame is the fabric basket seen in the middle, wrapping around the user and under the user's pelvic region. The user's weight is supported by the fabric basket, and the weight of the user is transferred onto the frame via the straps and is distributed evenly across the frame. There were 4 tests conducted in total: the weight load bearing tests, the walker roll time tests, the maximum incline tests, and the turn radius testing. The weight load bearing test was done using stacked weights for salt bags and was conducted up to 240 pounds. The walker roll time test was conducted using an elastic band for consistent force and various surfaces for various levels of friction. The maximum incline test was conducted using a raised surface and salt bags to determine how the height, weight, and incline interact to create a maximum safe pitch for the walker at any one of those given variables. And the turn radius testing was an error test used to measure the prototype's tendency to veer to one side. All the tests used the prototype walker as the subject and the standard market rollator as the control. The data for the weight test was recorded by taking the maximum tested weight. The data for the maximum incline was recorded in degrees, calculated using trigonometry. The walker roll test is measured in seconds and was determined through average times, and the turn radius test was measured in degrees using the same methods as the maximum incline data. The analysis shows us that the walker safely supports the maximum seated load of 240 pounds. It also shows us that the prototype took longer to roll across various surfaces than the control rollator. It had a maximum safe incline that dropped significantly as weight and walker height increased, and the walker has an average veering radius of 101.48 inches rightwards. The conclusion is that the prototype was successfully able to hold the 240-pound load with all weight placed on the hip support component. It accommodates users of different sizes, falling between the 5th and 95th percentiles, allowing for the user to stand. The walker is optimized for level ground navigations, future iterations adjusting the center of gravity and accounting for the difference made by a human user on an incline. While the JMP analysis indicated a significant increase in time, indicating less maneuverability, this quality can be used in an advantage as a safety feature to aid stability and prevent walker vibration.